Hi everyone. Today we are going to discuss about basics of Hilbert spaces, which we need for our further study of linear operators. So to start with, let us look at a simple example from the plane geometry. Let us take a triangle with vertices A, B, C, and the angle between the vectors AC and BC is theta. We know that the cosine formula which can be stated as follows: AC square plus BC square minus AB square equals to 2 times mod AC mod BC cosine theta. Here mod AC is the length of the vector AC, and similarly mod BC is the length of the vector BC. This is the cosine formula. Let us particularly take A equal to x1, x2, B equals to y1, y2, and C equal to the origin 0, 0 in R2. And now if you compute AC, BC and AB and substitute the values in this equation, let us call this equation as 1. Then we get that, so by 1 we get x1 square plus x2 square plus y1 square plus y2 square minus y1 minus x1 square plus y2 minus x2 square equals to 2 times length of the vector is x1 square plus x2 square and square root of it. Similarly, length of BC is y1 square, y2 square, square root of this multiplied by cosine theta. And if we simplify the terms here, we get that 2 times x1 y1 plus x2 y2 equals to 2 times length of the first vector multiplied by length of the second vector and cosine theta. Okay. So for simplicity, let us take, instead of A, let us write x as x1 x2, y as y1 y2. Then we can say that the left hand side of the above equation is nothing but the scalar product of x with y equals to, this is length of x multiplied by length of y cosine theta. So this is the first one is, this is length of x and this is length of y. Okay, so let us slightly change the notation again. So instead of x dot y, we write this as this way, bracket xy, and this length of x is, this is Euclidean length, this is called Euclidean norm, which we will be discussing at a later stage. So from this we can also say that length of y is Euclidean norm of y. Then the same can be expressed in this new terminology or new notation as follows. This is so this equation expresses the scalar product in terms of the lengths of the vector as well as the angle between the vectors. Okay, now let us look at particular cases of this. For example, if you take x non-zero, implies scalar product of x with itself is length of x square, so which is always positive. Here when we take y equal to x, theta is 0, then cos 0 is 1. Okay, so if you take the modulus for the equation, so this is mod xy, this is called scalar product xy less than or equal to Euclidean norm of x multiplied by Euclidean norm of y. So this one we can again write as scalar product of x with itself square root of this, and scalar product of y with itself square root of that. So this inequality is very well known as the Cauchy-Schwarz inequality. Okay, the third observation is if x is orthogonal to y, that means if the angle between x and y is pi by 2, if x is orthogonal to y, then by the equation 2 we will get the scalar product to be 0. So these are the three important observations which we can make from the scalar product of two vectors in the plane geometry. Okay, so our goal is to generalize these concepts to an arbitrary vector space. Generalize these concepts to arbitrary vector spaces. If we can do this, we can discuss angle between two vectors in a vector space, length of vector we can discuss, and inequality like the Cauchy-Schwarz inequality, and many more such things we can discuss. So that is the goal of this lecture. So to generalize this, we define a concept called inner product space, and before that we will discuss something called semi-inner product space and semi-inner product. So next we discuss about semi-inner product. So let us start with a vector space over a field F. Let X be a vector space or linear space over a field F. So F equal to either R or C, the set of all complex numbers. Okay. If there exists a two variable function, a function which we denote with this bracket from x cross x to F, satisfying the following axioms. The first one is scalar product of x with itself is bigger than 0. This we call as a semi-inner product. Instead of saying that function, we say from now onwards it is a semi-inner product between x and x. This is bigger than 0 for every x in x. So this condition is known as semi-positive definite. This condition is very natural because if you look at here, the scalar product of x with x we have observed that it is length of x square, which is always positive. Okay, so we want to generalize the concept of scalar product. So for that, actually we need this condition. The second condition, if you take semi-inner product of x with y, that should be taking semi-inner product of y with x bar. This is for every xy in x. Here this bar denotes the complex conjugation. Okay, so this property is known as symmetric property. And this is applicable only for vector spaces over complex field, because if you take x to be a vector space over real field, the semi-inner product of x with y is a real number. So when we take bar, it's not going to change anything. So this particular axiom is applicable only for complex vector spaces, and it is redundant for real vector spaces or real semi-inner product space. So this is needed only if f equal to the complex field. Okay, the third condition is since we are defining a new function on x cross x, function of two variables, and we know that on x there is a vector space structure or linear structure. Now we want to know how the new function that we are defining is going to act on, or how to it is going to act on the linear structure of x. So here, if you take two vectors x and y and take x plus y, take the semi-inner product with z. So this we expect as xz semi-inner product plus yz for all x, y, z in x. And the second condition is, look at alpha x semi-inner product with z. This is alpha times semi-inner product x with z for every xz in x and for every alpha in the field f. So these are the if the two variable function satisfy these three axioms, we call that function to be a semi-inner product. So is called a semi-inner product on x, and x with this semi-inner product is called a semi-inner product space. Okay, so let us look at a few examples. Before that, let us have few observations. The first one is, if you take a vector x and take the 0 vector, since x is a vector space, it contains the 0 vector. Now look at the semi-inner product of 0 vector with x. This can be written as 0 multiplied by any vector y, take the semi-inner product with x. So here this is a scalar, you take alpha to be 0. Now 0 into y is 0, that is a vector. Now by axiom 3b, this is 0 times, so this is 0. So this is true for every y in x. That means if you take the semi-inner product of 0 with x, that should be 0. Similarly, if you look at semi-inner product of x with 0, this is nothing but semi-inner product of 0 with x bar, and this is nothing but 0 bar, that is 0. So here again, so here this is a vector, so we cannot take bar, so this is 0. This is a complex number. Okay, this is, let us say, A, this is B. Now the second condition is, now if you look at the axiom 3b, so we specified that when you take alpha x in a semi-inner product with z, we got alpha times semi-inner product of x with z. Now if you look at, if you take scalar product on the second component or second variable, what will happen? So look at x alpha y, that is nothing but alpha y semi-inner product of x bar, where alpha is a complex number or real number depending on the field. So this is nothing but alpha bar semi-inner product of y with x. This is nothing but alpha bar here xy. So this is xy is in x and alpha is coming from the field. Okay, so these are very important observations for the semi-inner product. Let us look at some examples of semi-inner product spaces. Okay, the first one, let us take x to be R2 and here field is R. Let us take x to be x1, x2, y to be y1, y2. Define the scalar product of x with y as x1, y1 bar. So here real field, so this is x1, y1. You can easily check that this satisfies all the axioms of semi-inner product. So we can conclude that we can say that x with this two variable function is a semi-inner product space. Similarly, you can take x to be C2 and f as C. Define, let us take z as z1, z2 and w as w1, w2 from x. Define semi-inner product of z with w as z1, w1 bar. Then again we can show easily that this is x with this two variable function is a semi-inner product space. If you observe the earlier example and the present example, if you look at the vector, let us take z is 0, 1 in C2, then semi-inner product of z with respect to the above definition, this is nothing but 0, but z is non-zero. That means we can say that a non-zero, if you take a non-zero vector z, the semi-inner product of z with z may be 0. Okay, let us look at one more example. Let us take a and b to be real numbers with a less than b. Define Pn of ab as set of all polynomials in a single variable x which lies in AB. So this is set of all polynomials. P is a polynomial with complex coefficients of degree at most n. Okay, then if I take P and Q in P and AB, we can easily check that this is a vector space with P plus Q at T as Pt plus Qt. Alpha times alpha P at T is alpha times Pt. We know that this is a vector space defined. So this implies we can say that P of T as A0 plus A1t so on an t power n, Q of T as B0 plus B1t so on Bn t power n, where Ai and Bi are complex numbers I equal to 0, 1 to so on n, and t is a variable in AB, close interval AB. We can define a new function of two variables like this, summation j equal to 1 to n aj bj bar. You can easily check that this is a semi-inner product on P and AB. That means we can say that P and AB is a semi-inner product space. So here also if you take P of T equal to Q of T equal to the constant function 1, then the semi-inner product will be 0, but the function is non-zero. So these are three examples of semi-inner product spaces. Let us discuss one important inequality that we have already discussed in the beginning, that is the Cauchy square inequality for semi-inner product spaces. So let me write this as a theorem. So this is also known as Cauchy square Bunyakovsky inequality. It says that let x with this two variable function be a semi-inner product space. Semi-inner product space then we can say that modulus of semi-inner product of x with y square is less than or equal to semi-inner product of x with x multiplied by semi-inner product of y with itself for every xy in x. Or we can say that this is semi-inner product of xy bar xy is less than or equal to semi-inner product of x with itself multiplied by semi-inner product of y with itself. Okay. Let us look at the proof. There are two cases. Case 1, assume that semi-inner product of y with itself is non-zero. Okay, let us take a complex number which is arbitrary. Then we know that x minus lambda y semi-inner product is always positive. That is, so I am rewriting this again. Semi-inner product of x minus lambda y. If I expand this one, you will get semi-inner product of x with x minus lambda semi-inner product of y with x, that you will get as semi-inner product of x with xy bar minus lambda bar xy, plus the last term will be mod lambda square semi-inner product of y with itself. Let us call this as 1. Now to get rid of the mixed terms, the middle terms, we can substitute lambda equal to some number which depends on x and y, so that the middle term get vanished. So the suitable choice here is that let us take lambda to be semi-inner product of x with y divided by semi-inner product of y with y. We know that this is non-zero, so this makes sense. Hence, by star we can say that semi-inner product of x with x minus the first term will be, the first middle term will be mod xy semi-inner product square divided by semi-inner product of y with itself minus mod semi-inner product of y x with y square divided by semi-inner product of y with y, plus here the denominator gets cancelled, so you will get semi-inner product of y with y. We know that this quantity is always positive, so that implies, so we can cancel one term here. So if you simplify, you will get norm of semi-inner product of x with y square less than or equal to semi-inner product of x with itself multiplied by semi-inner product of y with itself. This is what we wanted to prove. This is case 1. Case 2, what will happen when semi-inner product of y with y is 0? This can happen in the semi-inner product space. We have seen examples. So in this case, let us look at equation 1. Let us take, let t be a positive real number. Take lambda to be t by 2 xy. So then if you look at equation 1, by 1 we can say that the middle terms will be mod x modulus of semi-inner product of x with y square. Two such things you will get, and anyway the last term semi-inner product of y with itself is 0, so what we get is semi-inner product of x with x minus two times t by 2 mod semi-inner product of x with y square is bigger than 0. So this implies mod x y semi-inner product square less than or equal to t times semi-inner product of x with itself. if semi-inner product of x with x itself is 0, then the left hand side anyway has to be 0. But if that is non-zero, and this is true for every t bigger than 0. On the right hand side it's a fixed quantity, whereas the left hand side varies with t. Now for larger t, also this is valid, hence we can say that this happens only when mod xy semi-inner product x with y is 0. This is what we want, because if the semi-inner product y with y is 0, the right hand side of this Cauchy square inequality becomes 0, and we have shown that left hand side is also 0. This proves the Cauchy square inequality. Okay, so let me quickly recall what we have done so far. We have given motivation for the inner product space. So we started with discussing semi-inner product space. We gave a few examples of semi-inner product spaces. Then we have proved the Cauchy square inequality for a semi-inner product space. Thank you very much.